Testing, 1, 2, 3.
And it was obviously a satirical joke, so then like the comments were full of either people or which I guess and then like I'm like
Oh, man. Okay, ladies and gentlemen, everyone, good to see you. Welcome back to EECS 404. It is, nothing warms the heart like listening to your conversations out there, eavesdropping, how dare I, and hearing lively debate about what were you able to implement, right? How are you doing this? How are you doing that? When you get deeper into the world of research, when you go to grad school, if you pursue a PhD, like you will eventually get to a point where there are no more teachers. There's no more Professor Yarger to create assignments for you, right? To give you this breadcrumb trail that leads you from one concept to the next. If you end up going deeper into academia, you will eventually get to the point where knowledge creation looks a lot like how it used to look. People walking around, finding each other, debating, and making experiments, sharing what they discover, right? If you've ever heard of publish or perish, right? Publishing in conferences, in journals, giving conference talks, presentations, traveling all the time. It's a really, really big part of academia. You are supposed to go do interesting, weird experiments, and then what you learn, you are supposed to spread. Because there's really no one out there to tell you how things truly are. Now that has to be you. And then, if you go that far, you might have students in your own undergrad class, right, who are putting their faith in you to deliver, knowledge on how the world works. So it's pretty cool to see, right? I think back to a lot of the earliest academies. You think of like Greek philosophers debating each other in the streets, right? And that's how it used to be done, and that's how it is done these days when you're on kind of the forefront of knowledge. So this is a long-winded way for me to say, yeah, good job. Keep talking with each other. Don't use it as a crutch, though. Use it as a way to expand your own knowledge and deepen your curiosity of what's going on and how to build an even better engine. And you'll be fine. If you look at where we are in the schedule, we are almost finished with that nasty, formidable, tough as nails homework 6. Homework 6, I think for many students, is the hardest assignment in the course. Homework 7 is, tough, kind of for different reasons. And I think it's a little bit more satisfying of a homework. So I think it was easier for me to make, not really easier for me to design, but I think you'll really enjoy it. So if you haven't really gotten very far in homework 6, you're not toast yet, but things are definitely getting a little bit crispy, okay? And, I think you should feel a little bit of an impetus to get a move on, get caught up if you can. And remember, halfway through homework 7, we have spring break. Now, I want you to be able to relax during spring break, but hey, if you're perpetually a week or two behind, well, you might have to spend that, all right? Catch up. Or you can accept that, hey, you're just not going to finish homework 9. You're skipping homework 9, 50 points gone. Extra credit will help patch that hole. Still possible to get a reasonable grade if you don't make it all the way to the end. All right, do a good job on the exam. You'll be fine. All right. So, yeah, how's homework 6 going? I'm kind of curious. It's still like one of my least favorite homeworks in the class, because I think, maybe the collision detection algorithm isn't quite as precisely described as I could. I should probably make a little animation video to help people understand what you need to do and why you're doing it. We do have the algorithm written up at a high level in the assignment spec. If you're missing that, make sure you look at it. But do the best you can, and know that if homework 6 is a disaster, homework 7 is going to have you getting rid of a lot of that gameplay code, collision code. In homework 8, we're going to take the collision code you wrote in homework 6, and we're going to replace that wholesale with the wonderful Angry Birds Box 2D physics engine. So I hope you look forward to that. Some people do because they don't really like their code, and some people, by the time they get to homework 7, have grown quite attached to their baby. Okay, so I'm curious which one of those sides you will fall into. How many of you are starting to grow quite attached to your code base? Right? It's I've definitely felt that before. Right? The auto grader for this course is quite a hideous code base, but it is mine, and it does the job. Right? And so it lives on, and I can't feel anything but a kind of a sense of pride in it. Even as hideous as it can be in some places. So today, what I want to do is I want to cover a couple topics. I want to cover the quiz number 3. We had a few problems on quiz number 3 that kind of wrecked quite a few students. I want to go over those, and I want to kind of explain what they're going for and what you should take away from them. I want to finish up our talk on components. Components. Why components? Well, a component architecture is an incredibly powerful thing, and it is very standard in the world of game engines, and you'd better understand it because you're going to have to make it. You're going to have to bring it to life, top to bottom, in a very authentic way. You are, when homework 7 starts on Monday, you very much are recreating Unity, okay? This is to say, after you finish homework 7, I'd be pretty comfortable saying, yeah, this kid did a good job. You should go work at Unity, right? Or go make your own engine, Unity competitor. And then what I want to do is, just like I promised, I created a little new lecture. It's not as lengthy as I wanted it to be, and there's some topics I had to cut, but there are a couple fun things and ideas I want to show you in here. The world of performance is really where computer science starts to feel like a science, because my goodness, you need to experiment a great deal. And you can make predictions about what will happen, but the situation is made very mushy by the never-ending list of optimizations that compilers these days may or may not apply. And so we'll take a look at that, and we'll take a look at profiling and how you can use the profiler. One of your most powerful weapons against homework 6 and the fight for more performance is your profiler, right? You don't always know which code is really bottlenecking you. You don't know which code is running slowly. Sometimes you can put a lot of effort into some code, and you think it runs really fast. Oops, nope, sorry. There was something you got slightly wrong, and it's actually a bottleneck. It's horribly slow, okay? So I'll show you some examples of that in just a bit. I want to show you one of the most impressive engines I've ever seen. Of course, it comes from our beloved AAA game studio, Ubisoft, okay? They need your energy right now. They're holding on by a thread, and if you have any positive vibes, you need to transmit those vibes through the air to Paris as soon as you can, okay? Because Ubisoft is looking like they might not have much time left. But I'm going to focus on a really, really cool piece of technology that they kind of first unveiled in 2011. I'm an Adobe Flash child, okay? I grew up, it was my second game engine I ever used after GameMaker. And if you've ever heard of a website or a culture referred to as Newgrounds, I was a part of that in the early days. I won't tell you what games I made because kind of embarrassed, but they were somewhat popular. I'm kind of anyway. Enough about that. Adobe Flash is an engine that will come up later, but one of its great strengths is that it allowed animators and artists to very quickly, in the same program, go from making beautiful vector art, which, by the way, is vector art that uses math and not kind of rasterization, not bitmaps, but SVGs, mathematical expressions to express artwork. What does that mean? That means it has infinite resolution. You can scale and zoom, and it's just gorgeous, crisp all the way. Well, as you can kind of see here, it's almost the perfect engine for animators who want to be animating build objects kind of like you would in Adobe Illustrator, and then immediately start associating logic and code with those things you've just drawn. And UbiArt is the kind of game that is spectacularly good if you want to make a cartoony game. I want to show you a trailer for Rayman Origins, I think, or maybe this is Legends, we'll see. And then I want to show you a little demonstration video to kind of, so you can see just how nice this engine is to work with. Let's take a look. Testing, okay. Okay. Here we go. Right? So you've got this situation where you can very quickly going from drawing up a character or an object to then kind of breaking this object up into a bunch of different objects, right? This artwork, as you see here, you can quickly start kind of defining the parenting structure. You can start creating bones, okay? You can create these colliders in all these different shapes. And then you can start parenting them, right? So the arm bone, the elbow bone is going to also control and parent all of the finger bones. And you can see the animator kind of testing these parenting relationships right here. And you can just kind of very quickly move into really complex, bouncy, juicy 2D animations like this. I want to, yeah, here's a really cool video demonstration. I think, is this GDC or something else? I don't remember. But let's take a look. This, I think, yeah, let's take a look at what they say.
I'm ready to see. Yeah, ready. If you look at the editor right now, I'm going to do some stuff. Julian's going to play around. And basically, he's walking around. This is the game, right? Well, I mean, actually, it's the editor at the same time. So he's playing, but you can edit off the fly. That's crazy. It's a really crazy editor. So, I mean, okay, Julian, we don't like these guys. They're in the way, aren't they? Stand on for a sec. No. They're kind of. Oh no! Wait. Oh, sorry. I undid it. Wow, that's dirty. That's dirty. So this is the engine. This is the game running in the engine. That's a level that you have. Now I'm just gonna hide the art layer for a second.
Oh, okay. Yeah.
This is what a level designer sees every day of his life on Rayman Legends. Okay. This is all you get. So we're looking around. There's this collision. There's some gameplay elements and the characters.
Right.
Now, what's interesting to note is the gameplay collision is actually pretty beautiful already. it looks like what it's supposed to be. It's got grass, it's got rocky surfaces and everything. Now watch this. This is pretty cool. I like this. So we've got a grassy surface on top, right? Okay. Simple. But what if we make a 90-degree angle? If it's grass all along, it's going to look weird. Gotcha. But we make a 90-degree angle, and now our engine is just as good. Okay. So that's basically how it works. And he's playing while I'm editing. I mean, we don't necessarily do this as designers because we're always busy like one-on-one. But it's just the flexibility that I can be jumping in and I can be working on it. It's in the game itself. And if Julian jumps into this cage, I can show you the exact trajectory that he's traveling. So if he jumps and I say, okay, stop that, I'm just going to put a platform here because that's the perfect jump height. Right now, I've made my level. And he has the perfect jump height, but he does that really crappy short jump. And now he's got a leg up to get that cage. So honestly, this is like...
Okay, right? So this seems like an animator's dream, actually. And this is the kind of magic that Adobe Flash back in the day really did give you. For people who were hybrid, a little bit of programming knowledge, a little bit of art and animation knowledge, it was perfect. And this is probably the closest I've seen to recapturing that Adobe Flash magic. If you want to do this kind of thing in Unity, well, you need Unity for the logic, for the game objects and structure of your game, for the camera, but unfortunately, you have to use a separate program. You have to use an external program like an Illustrator or a GIMP or an Adobe Photoshop. And then you have to deal with things very separately. You have to import all that stuff. The iteration time is wildly slower. You don't have much freedom, and so it makes me very sad. Rayman Origins. It was used not just on Rayman and not just for cartoony games. This is a game called Child of Light. Quite beautiful. Let's take a look. Right? So this was the kind of engine that could support other art styles and other kinds of games as well. And it became very valuable to Ubisoft. They were able to make some licensed cartoon games. Gravity Falls game they made used it. Rayman series tends to use it these days. Unfortunately, it didn't really change Ubisoft's fortunes. And even worse, UbiArt, despite how often they were talking it up and showing it off and using it, was never open sourced. It was never made public. Okay, this could be the next Adobe Flash, but if Ubisoft goes bankrupt, then that's it. All right, maybe it will stay buried forever, or maybe someone will buy it and then release it or something like that. Could be kind of cool. So anyway, it's just another example that these days, if you want to compete with Unity or Unreal, the way to do this usually isn't by making a generalist engine. It's by making an engine that is very specialized towards some type of game. In this case, UbiArt, it is specifically tailored to be an animator's dream game engine. Okay? And that's a pretty rare thing. That's still a rare thing. Like UbiArt is great, but it's not available. Okay? So who knows? Make your own version of that, and maybe you've got a winner. Okay, I don't have any announcements really, except the fun fact that you are over halfway done with the quizzes in this course. With the completion of homework 3, you only have 4 and quiz 5. So the course is not that long, it's almost done, actually. So the semester is going to start going by really fast very soon. And Lua, a very fun topic, right? Learning a new, powerful, classic, very beloved programming language is going to start next week on Monday. So I hope you will be ready for that. It's a lot to learn in just a couple weeks for homework 7. But thankfully, Lua, part of its charm and legend, is that it is a very minimalist engine. makes it very easy to embed. And so long as you understand a few foot guns that Lua has, you can get very comfortable with using it very quickly, okay? All right, so quiz number 3 had an average of 85%, but some of those problems were really wrecking about half the students. So, pass rates, clear rates of about 65%. And so I want to show you some of these, and I want to talk you through them a little bit. Here was a problem. 65% of students got through this one. This is a question in which you kind of get to see a very common problem you run into when you're dealing with game engines, when you're making your own and you're trying to make things very fast. You see this code belonging to an image database class, and the function is called getTexture. It returns an SDL texture pointer. You give it a name. Okay, it's pretty clear what this is meant to do, and there's a very good chance you wrote something similar to it when you did your homework 5, and if not, homework 6, where performance was a big problem. Here we have a kind of a basic setup for us kind of creating a path to an image. We check whether that image exists. If it doesn't exist, we kind of error out. And so this all looks pretty correct. This should look very similar to what you might have written. Now, one thing here to note, though, is that there's a bit of an issue. This function right here, image load texture, it is going to take the path to a file. It's going to take a render that you provide, and it is going to give you a texture. It's going to load that texture into memory, send it to the GPU. All right, loading something from disk and sending it to the GPU, both of these things are slow. All right, very slow. They're the kind of things that you would like hide in a loading screen, probably, or you would try and make as fast as possible. The question asks, like, hey, there's something wrong with this code, and it asks you what you think is wrong with the code. And you've got some options. Like, one is correctness, I think. Not really a correctness issue here. This should work. The big issue is performance, okay? Huge issue. If you have this kind of thing happening in homework 6, I think you're going to struggle a little bit to pass your test cases, but your performance test cases in any case. But yep, so kind of a tough one. I'm not entirely sure why it was tough. Maybe maybe I should rewrite the question or something like that, or change the answers. But let's look at the second one. Okay. In order to speed up collision checking, you implement a region-based spatial hashing data structure, the one we've been talking about in class. So if you haven't kept up with the lectures, then this would be a hard problem. It allows one to very quickly basically search, hey, in this region, in this area, what actors exist? Give them to me. I want to check their collision against my player, maybe. It appears to work well, but there are some issues with this approach. And in lecture, we talked about a few of them. And I think I can go to the quiz section here, and I can actually kind of show you. I can kind of show you what the possible items are. Spatial hashing. Okay, let's go in here. Build. Okay, come on. Hello? What? Hey? Am I looking at the wrong one? Or is it not capable of searching through these? What on earth is happening? Okay, correctness, performance. Okay. Is it not in here? What? All right, we're skipping this one. Basically, in this question, there were a bunch of possible answers. There are a couple things wrong with spatial hashing. One, there are pathological cases that can appear where if every actor in your entire world decides to go to the same region, you have no performance benefit whatsoever because you're going to look up all of the actors in that region, and you're going to have to check all of them. There's another issue, okay? When you add an actor or when you want to remove an actor, if you allow actors to resize their colliders or their triggers, suddenly your region system might be invalidated. You might have to go and rehash everything to make sure that's going to return correct results. Another issue is that if you happen to have a very large actor, based on the implementation we told you about in class, if you have a very large actor and then all the other ones are small, your region size will probably be determined to be very big to handle that big actor. But that will be very non-performant, okay? As the smaller the regions are that you decide on a small region size, the more performant the entire data structure becomes. The other options are nonsense. And that's the most important part. You're told to check 3 boxes and the other 2 make no sense at all. And so you can also answer the problem effectively by doing it that way. I'm not sure what's going on with Canvas's quiz. It's just not searching through there for whatever reason. Here's a fun one, okay? This one is kind of similar to some of the questions you find on the exams. You have a make file. We're testing whether or not you actually kind of understand what's going on with your build systems. And make files are kind of a nice, clean way to look at the situation, because you don't have to worry about Xcode UI. You don't have to worry about Visual Studio's UI, which is always kind of changing and shifting. Okay, here we have Clang++. We have a folder, a source folder with a bunch of CPP files that we will include in the build. We have C++17. What does -I mean? Tori, what is that?
Include.
Yes, but be more specific.
Including header files.
Yeah, the -I will be followed by some sort of path, and that path is going to be added to the list of paths that our compiler or our preprocessor should search when we do that include statement at the top of our files. Okay, include map-helper.h. Well, it needs to know where it should look for that thing. And if it fails to find it, we don't compile. And so by doing all these -i's followed by path, we're creating a bunch of directories that we're going to look in. And so we have the root path, we have the source folder, we have the SDL2 folder, SDL image, mixer, TTF, and then that's the end of our headers. We then have -l followed by a library name. And that is telling us which libraries to link against. On Linux, usually these libraries will be installed in a global location on your machine. And so you can kind of assume that these are installed. Anyway, -03 for optimization and -O for Game Engine Linux to name the executable. So you can kind of see this structure. And the question down here is gain access to the function piece. You want functionality within SDL image.h. So which of the following include directives will work? And you have a few options. So you can do include SDL image, then SDL.h. Let's go ahead and look at this. All right, would this work? Anyone know? Is there any folder, the root folder, for instance, SDL image? Let's look inside of SDL image. What's the side of SDL image? It's going to show us. All right. Do you see an SDL image.h file in here? So the path just failed. This include just failed. Okay. There's no way to follow this path from any of these directories that we listed in here with this .I. So move on to the next one. Include SDL image.h. So we can't start from the root. Okay. This one is out. The root is out. Source, we're not going to find that folder in here. We're not going to find an SDL image.h file. What about SDL2? No. SDL image. Okay, let's try that. So if we go to SDL image, and I think we are currently in SDL image. SDL, do you see the SDL underscore image.h file? No, so that path just failed. And unfortunately, we don't go in here. We don't go into the include. If this said SDL image include, then that path would work, but it does not. So now we have include /SDL image.h. Okay? So now, will that work? Well, we have a path up here called SDL image. And if we go into SDL image, right here, we are now inside of SDL image. Let's start our search from there. What was the path? Include. Do you see an include folder? Yes. Okay, what's inside the include folder? Next part of the path is SDL image.h. Do you see that file? This checks out. It works. All right. And so we check that box. And then we have include SDL image, include SDL image.h. This is just this one, but starting from the root repository, which is one of our places to look. So check that box. Cool. Not too bad, right? You just kind of read through it and you just kind of test each of these, and that's it. Okay. You know, that used to confuse me like crazy. And now these days I wonder, like, how was I ever confused about this? I think it's partially because there are just a handful of things you just have to know. Like, what on earth, dash capital I? What? Weird, right? You're not really used to seeing strange things like that. Final question I want to show you. Okay, SDL notifies us about inputs and events via the event queue. You can see an example of this event queue here. Jog your memory, right? We need to drain this because we will freeze the program otherwise. This is a classic pattern seen in many contexts. It nevertheless has some downsides. And we kind of talked about this. This is one of the reasons we built the input manager in Homework 5. You don't have to do that, but it's going to make your internal programming of your C++ engine easier. And when we create the Lua input system, it's going to be easy, plug and play, like easiest test set in the entire course, test suite. And otherwise, it might be kind of tough. At some point, you're going to want to implement that input manager. But one downside is that passing the filled-in event object E around to the far corners of one code base, which is what you have to do if you are not using an input manager, is kind of annoying. It's awkward. It's going to make your code look hideous. You're going to have you're going to be passing this E object around everywhere into functions that probably shouldn't need it. Pull event will pop the queue, right? And if you try and look at and read the queue by calling this function elsewhere in your code base, well, sorry, every time you call this function, you're losing an event. And so it isn't really possible to treat this function like its own input manager the way you might want to. Possibility of losing and dropping events when your program is under heavy load. That never came up during lecture. It would be catastrophic if SDL allowed this. No one would use SDL ever if it was dropping events. It could be a really important event, okay? And if we used SDL and it could drop events, we would be hopeless. There's nothing we can do to protect our users from that. Not much we can do. Compatibility, build, and compiler issues when integrating with other libraries. SDL might be hard to integrate, but it's not because of this particular event queue design. You find this in Python, and if you bring SDL to like other code bases, you'll be fine. Like, this is just not a thing. It just doesn't make any sense. So this is another one of those questions where you can either know the answer or you can know what isn't the answer, and you will get those points. Lack of built-in convenient lifecycle state checking. If I want to know if my right arrow key was pressed down, but on this exact frame it was pressed down. It hasn't been held, it's been pressed to this frame. What do I need to do to know that using the event queue? You can figure out, well, okay, hold on, a different question. You can know if an event comes in, right? SDL key down event, you know it was pressed to this frame. How could you ask yourself whether it's currently held or not held? Yeah.
You have to like store some sort of like historical knowledge.
Yeah, you have to keep some state. You have to keep like a Boolean. And then if you see a key up event coming through and it's for the right arrow key, you can set the Boolean to false. If you see a key down coming through and it's for the right arrow key, you can set it to true. But you have to keep this extra state. You have to do this for every key you want. And so the lack of good lifecycle functions that the input the input manager provides is going to be, it's a bummer for the queue. Okay, you usually need to build some stuff on top of this. It kind of makes you wonder whether SDL could like add this, and whether that would be such a nasty thing for them to do. It'd be kind of nice, I think. All right, maybe that's too high level. It's more high level than what SDL wants to do. Okay, any questions about the quiz? Cool. All right. So I want to finish up our talk on composition, and then I want to talk to you about some very tiny optimization ideas. And it's not super deep, so don't get too hyped. I think it was up till about 3 a.m. last night, and yeah, I didn't get quite as far as I wanted to. So last time we looked at this idea that all of these game engines are using components, and it doesn't really matter if you are in your own game engine in this course, or if you're in EECS 440 Unreal Engine, or if you are in EECS 494 and you're doing Unity engine. All these engines are kind of using components, and composition is just everywhere. The usual way to reuse code and create logic once and reuse it everywhere is to use inheritance. And you create this ISA relationship structure. A bear is a mammal, which is a living entity, which is an object. But ISA relationships, these kind of inheritance-based hierarchical relationships, these tree relationships, are a problem, okay? They can express some things, but then they often get tripped up. So we can't use multiple inheritance. It is banned. We run into this problem all the time, like when you're organizing things into folders. That is a tree structure. It's going to have this problem eventually. And so we decided that ISA relationships are the way to go. We want to be able to make components that are not about what you are. They are a HAZA relationship, right? So the duck example. A duck, is simply something that can quack, and it walks like a duck, and it looks like a duck, and because it has these attributes, we consider it a duck. It's much more attribute-based. So likewise, we can write a component that's called sine wave movement, and now we can give that component to anything we want. Flying enemies, flying pieces of ground, platforms. We can build objects by creating components and then just giving our different actors different collections and combinations of components. And this can be quite nice compared to the more rigid and stiff and difficult to manage and inflexible inheritance-based approach. In order to get past some of the issues with dryness, you can use inheritance with composition in order to maintain a really nice, clean, dry code base. Then as you make more components, as you write them better, you make them more flexible, you make them less buggy, you end up with this massive toolbox of components that are good at working together and very easy to use for your non-technical teammates. And so this is exactly what you tend to see on small games, yes, but also big games. A lot of proprietary engines will implement some sort of composition-based system. For instance, on the Sims engine, right, where you could kind of add components onto objects, and that would give new interactions that the Sims could do on those objects. This is also the way that EECS 298 and the games, the platformers we make in that course do their thing. I feel like we have a little extra time. Can I show you an EECS 298 game? Let me see here. umich3d.com. Okay. And let me see here. Which game will be really nice? Which game has a lot of this? I could just show you mine, but maybe I will at the end if I've got a lot of time. Escape the Midwest, Gabe Saves the Train. I'll let you choose. Gabe Saves the Train? Escape the Midwest? Okay, let's do it. Okay, Eugenia Hernandez Martinez. So what you're going to find is that we have components that allow you to talk to something dialogue interaction components. And we can put this component onto anything that we want, and we can talk to it and get dialogue with it. There are other things like locked doors.
98. Escape the Midwest.
A reminder, the student drew and modeled everything in the game, and they also did their voice acting. They did get music, I think, from someone else. So, kind of cool. They only had 2 weeks to make this. So, they also animated the characters, too. So, hold on. Oh, goodness. All right. Hello. Finally, I've been trying to wake you. There's only so much my wooden arms can do. You're going to be late. The bus leaves in 10 minutes. Hurry. Okay, let's get out of here. Oh, and don't forget my scarf. Okay. So, you can turn any object in the entire game into a checkpoint just by... Wait, hold on. Okay, just popping a checkpoint component onto the object. In this case, it's a flag, but it could be, I don't know, it could be that seal over there, right? Both of these seals have what's called an interaction dialogue component, and that component can be customized. For instance, we might want both of these characters to have dialogue, but they have different dialogue. And sometimes you can put on multiple components so that they'll say one batch of things and then they'll wait a bit and then they'll talk to you again. Or maybe they'll request an item from you, and then after you provide the item, a second component is allowed to run that allows them to talk to you and give you the solution or something. Hey pal, enjoy your trip. We can hang out when you get back. Be careful with the ponds. They're super cold today. Howdy neighbor, you're in a hurry? Cancun, huh? Can't blame you. Take some warm pie. Look at that. So we had a component where you talk to the character, and then a second component was there that enabled a game object, this pie, which gives me an extra life, okay? So these platforms have a component that makes them shrink a few moments after you've touched them. Okay. This water is a game object that has a component. What do you think it does? It's a component called KO on touch. And if anyone touches it, they die immediately. Okay, so I think you get it. Down here is an invisible plane, and when you touch it, it also has the KO on touch. Dead. Rest in peace. Okay, so do you get it, right? You can create an affordance, an interaction style system where in order to make objects do things like talk to you or kill you when you touch them or ask for an item or spawn things in or whatever, transport you, warp you around or shrink or whatever. You can create components that do these things, and then it's as easy as just popping the component onto the object. Same thing with The Sims. So, one big question for us, right? Normally, this wouldn't be very important, this question of how do we get composition? But this is game engine architecture, okay? You can't just use Unity or Unreal to get composition. You've got to make this yourself. So, how do we get composition? Well, for most people, you would say, grab Unity, because Unity is entirely based around composition. You will have game objects, also known as actors, in your scene, and every actor, every game object is only going to do the things that they can do by having a component that does it. Every game object will have a transform component that is guaranteed, it is required, but all the other components that you may or may not have are going to make things happen or make things not happen. You can turn them on, you can turn them off. Each one of these component types can be customized once you put them on to a particular game object, and you can reuse them across as many different game objects as you want. Same case with Unreal. You can get composition and all the benefits it provides by just choosing to use Unreal. Here's an example. This is kind of a recreation of one of our old labs in the Beister building. Wait a second. I want to show you one more thing, okay? Can I show you one more thing? I want you to tell me if some of these EECS 440 projects look a bit familiar. Just a little bit familiar, okay? There's just something about them. Let's go to Exhibition. Which room is this? Exactly. So this is a room recreated. But you can't just recreate the room visually. What's really important is that you make it interactive. So light switches, the whiteboards you're actually able to draw on. NPC characters you can actually talk to and get a little bit of dialogue on. Fire alarm, right? Way back there in the corner. There it is. Doors you can click on to open them up or go through them. Stuff like that. The interactivity of it all, a garbage can, is really, really, really important. So you can have a little brick actor here, a little white block, and you can say, well, that's my light switch, right? When you click on that light switch, you're going to see it has two components. This is the name of the actor. Here is one component, the static mesh component. This is what's going to give you your visuals, your physics, your collision detection. Unreal Engine loves big, chunky components that do 1,000 things. And you have a second component, AF toggle actors. It stands for affordance. It's kind of a synonym for interaction. Think of this as interaction, toggle actors. When you click on it, it's going to turn actors on, off, on, off, on, off. And what's happening here is the actors to toggle that we're turning on and off are these point lights that are in the ceiling. What did you just do? You just made a light switch, just like that. And if this particular component already exists in your project, you made the light switch without even writing a line of code. It is amazing, okay? Super, super powerful. So composition and Unity, right, and Unreal. In this course, you are actually going to have to make your own component architecture. It is literally the entire point of Homework 7. So if you look at this particular bit of gameplay, you'll see that there are a handful of actors in this scene. Some of them are visible, like Donna. Some of them, like the donuts, the donut projectiles, they're spawning in, they're despawning. You've got enemies that are infinitely spawning in. They have a component that's making them move to the left on this kind of sine wave. You have this kind of health meter up there. That's a component. That is a bunch of actors that are communicating. And you also have an invisible actor that is right over here, and it's responsible for spawning in enemies to come at you over time. If you look, there are also two actors that you might not have realized are here. You have a beautiful scrolling background that is infinite. If you don't know how this kind of thing is done in games, it's very, very funny and very clever. I wish I could show you a zoomed out view here, because here's what's actually happening. We have an actor called background 1. We want that background to be visible, and we want it to move. And we also want it to, be infinite. So we have three components. Each of these contributes to this. We have one component called transform. It is of type transform, and it holds an X and a Y value. We have a second component called moving background, which is going to kind of constantly move these kind of toward the, it's moving these toward your left, okay? And what's happening is as soon as one of these objects gets too far to the left and goes off screen, what do you think happens? It leapfrogs back. And then when the other one gets back, it leapfrogs and leapfrog, right? And as a result, you can use two game objects to create an infinite world. It's pretty amazing. They then have a third component type, a sprite renderer. And we actually tell it which PNG image file to render. And this component right here, and this component, transform. The transform and the sprite render are shared with basically every other actor that you can see, okay? The only thing that really makes those background actors unique is the way it moves and the way it leapfrogs. And so they both have this moving background special component that no one else really has. Does it make sense? If this makes sense, you're already done with homework 7, okay? Homework 7 is all about kind of making these components come to life and able to do what they need to do. So how do you build a composition framework? Because you're going to have to do that kind of soon. Well, there are a couple things you can try. Here is a purely C++ based approach. You can create a class called component. Now, you will never use this class. This is a kind of pure virtual parent class whose only purpose is to set us up for polymorphism, i.e., I want to be able to have a list, a container, a vector of a bunch of different types of components. But I'm going to say it's a vector, carets, of type component with a capital C, and that means I can put any child component type in there. And I can call any of these virtual functions. That's polymorphism. You're able to treat a bunch of different things in a standardized, consistent way, which is really, really crazy elegant. It can be a little bit non-performant, though. Polymorphism has some performance drawbacks, but it's very nice. So you could have a base component type that has the start, update, and destroy functions. If any child class derives from this, then it will have these guaranteed, right? You don't even have to worry about it. They're going to have these 3 functions. They might not do anything, but they're going to have them. You can then say, well, I want a particular type of component. So I'm going to create a transform component, right? Which typically stores your position data, your rotation data, your scale data, some other functions, some parenting information maybe. We don't require any parenting in technology in this engine, but some students add it in the final 2 weeks for the custom research feature. So we have a new type of component here. It's going to store some data for us, XYZ, 0.3. It provides some functions, so you can actually edit that data if you want to after the fact, and you can get that position data if you want to. You would make a much bigger one, of course, if this were real. But you also not only have component-related classes, but you have an entity, right? You have an actor. In Unity, this is called a game object. In Godot, this is called a node. And this is basically a container for your components. You have up here a vector of type component, component star, component pointer, and you then have some lifecycle functions of your own. So when you want to update a character in Unity or Unreal, what do you have to do? Well, you need to go to all of the components it has where all the actual important logic is, the stuff that does things, and you have to call those functions, okay? You have to call update. People get into Unity and they don't think about why does my update function get called seemingly out of nowhere 60 times per second. Well, it's Unity that's calling that function for you. In Unreal Engine, same thing. You have event begin play and event tick. That's what Unreal calls the update function, event tick. Unreal has to call that for you. No one else is going to do it. You're not going to do it, okay? So in Godot, it's called process. I really wish they would all just settle on something. Wouldn't that be nice, right? Whatever, all right, whatever. But you have to go through and you have to call those lifecycle functions on every actor. And every actor might have 0 components. It might have 1 component. It might have 1,000 components. You need to call update on all of those. And then you have to worry about things like fixed update. You have to worry about things like the start function. Here's a fun one. This entity class, your actor class, you're going to need a way to add a component and return a reference to that new component you added. Here's a kind of a fun way to do it. You can template, okay? You can generic this particular function so that you specify some sort of type of component, T. You then allocate space on the heap or somewhere for that component. You probably don't want to do it this way because what's the problem with this right here? I think William was talking about this earlier, complaining about this on Discord. What happens, William, if I want to create a new component and maybe in my game I want to create like 10 sprite renders? Well, if I end up creating 10 sprite renders using this line, where are those sprite renders going to end up in memory?
Just random places.
Yeah, just random places on the heap. That's a big pain in the butt. It's very slow. It's going to work, which is good. But when you go to grab one of these to call update on it, you would really be very happy if the cache loaded in the next few. So you could call those quickly without having to, go up the memory chain and, to the hard disk or something awful like that. So this is maybe not the most performant code ever. But that's another thing. Get it right and then make it fast later, okay? I'll prove this to you. It's the best idea in just a moment. But we're going to create a new component. It's on the heap somewhere. We have the address stored in our new component pointer. So that's good. We're going to put that into our components vector. This is going to be contiguous. So that's... well, at least the pointers are contiguous. Pointers are going to take you all over the heap, so I'm actually not sure how useful it is. You need to call start, okay? You need to call that begin lifecycle function. No one else is going to call it, all right? And so this is the equivalent of Unity's start or Unreal Engine's event begin play. And then often you will create a new component, you'll add a new component to an actor, but then you want to customize its features. So you can't just stop here, you need to return that pointer, that reference, so that the code that added the component can then customize the component to make sure it's going to work the way they want. All right? So makes sense, right? This code, okay, these components, in this course, they're not going to be written in C++. These will be in Lua, okay? So that's a pretty big, important difference here. Okay, and then you might end up with something like this. This is just some dummy code to like prove it's all working. And you can actually download this and compile it if you want to via that bit.ly link. I think it's not broken. I think it's still valid. But we can have an entity, an actor, we would call it in this course. We can add a render component. We can add a transform component. We can then call get component to get a reference to any particular type of component. We can then call that component's functions, like set position to move it to a new place, and we will see that it now has that new position. If we call update, then maybe if we have a rigid body, the transform will start to fall. Okay? Or if we have a sprite render, maybe it will be rendered to the screen. There you go. Okay? Not too crazy. Not too crazy at all. A summary here for all of this, for today and for Monday. Okay? Components are awesome. They are fantastic. They are, God's gift to game dev, seemingly. And they are awesome because they're very flexible. You can add them, you can get rid of them, you can customize them all at runtime however you want. You often have components that are talking to and manipulating other components. And it's just very, very nice. They can be mixed and matched at runtime, as we said, and it's super, super good for any scenario where you need interactions on certain objects, like you just saw with the EECS 298 games, okay? EECS 298 available next semester. Register now, okay? Wait, when does registration happen? Does anyone know? How many of you have taken 298 already? Anyone? Yeah, good job. Did you have a good time?
Yes, I enjoyed it.
Very good. It's a flex tech. Definitely take it if you have time. It will make you a much better dev, all right? Even if you don't become a master 3D artist, you'll have a very good feel for how 3D models get imported, how they get constructed, how they get messed up, and how to fix them when you want to use a really cool model for your games. Okay, so super good for any sort of adjective situation as well. So when we say, I don't want a panda, I want an ice panda. Well, the panda uses inheritance to get spawned in and reused. But the ice panda, that ice adjective, is a component that can get added on to any noun. Okay, so adjective system in Scribblenauts is just totally implemented by a composition-based approach, which is why ice works on anything. You can have an ice bear, ice panda, ice snake, ice burger, okay? And you can add as many as you want. A royal, so you get the little tiara. Flying, so you get the flight behavior. Big, so you get the larger than normal size panda. Just add 3 components onto the noun that you spawned in. Done. Easy. Okay? So, and it can work very well with inheritance. So don't forget about inheritance when you're using components. You know, just try and understand how you might use them together. All right? Do you have any questions about the topic? Okay. Good. Good stuff. All right. So what I want to do now is I want to I actually have a kind of a fun question for you. All right. Now, I'm going to remind you that I am actually kind of not that great at optimization myself. It's really fun and I enjoy it. I just don't do it very much. The kind of games I make are not bottlenecked by runtime performance, but by dev time productivity. I make low poly games that, unless I'm going to the Switch, okay, aren't going to have performance issues. Okay, you know, I really want to get a Nintendo Switch dev kit for Wolverine Soft Studio. Wouldn't that be awesome? The amount you learn optimizing things in Unity, in Unreal, when suddenly, you know, everything was running at 90 hertz, 90 FPS, and then you bring it to Switch and it's running at like 13 frames per second. It's like the number of things you'll learn about your game and what makes it slow is crazy. So I think that'd be super cool. All right, have you ever heard this phrase before? Okay, and not just from me, right? So apparently Donald Knuth, a very famous computer scientist, is like often said to be the originator of this, but it actually came from a guy named Tony Hoare. So you've got premature optimization as the root of all evil in programming. And if you don't have a good sense for why this is true, I've got a question for you, okay? I've got a challenge for all of you. And I think you're going to nail this because, like, we got some cracked students in this semester. Like, ridiculous, okay? And some of you are cracked, but you don't even know it, all right? It's not always flashy being good. So here's my challenge, okay? What does the following code do? What is it for? If you had a name for this following function, what would you give it? It's a very well-known function. Here it is. I'm not very good at bitwise manipulation myself, but I'll try and give you a notion of why this works in just a moment. I'll try and probably fail. A big hint is it takes an integer and it does something to it and it returns it. Yes. Got it. A negative operation? You're close, but it's not a negation operation. Anyone? I want you to imagine you are on a development team and you're trying to fix some bugs and you know the bug is around here somewhere and you see this function. What on earth? Can you even deal with this function? It might take you some research. You might have to ask AI and pray that they get it right and don't troll you. All right, to figure out what this is doing. Or you might want to look up who wrote it and ask them. And then you discover that they left the company 2 years ago. Damn. Right? So any final thoughts? Anyone want to take a guess? We got negation, very close. Yep.
Absolute value.
I'm going to show you another version of this exact same function. It's just written a bit differently. Can you now tell me what this function is and what we should call it?
Yeah, with the absolute value.
This is the absolute value function. Can you believe it? Both of these are absolute value. And this bottom one, if you don't see it, if you don't like ternary operations, like I don't, like I can never remember which one of these I do if it's true. Just never remember. It's arbitrary, man. I prefer this, okay? Now you can see it, right? Okay, this is a absolute value function. I've got another question for you, okay? If these are both absolute value functions, why on earth would you write this one? Another question is, well, which one of these is uglier, okay? Who thinks the top one is uglier, right? Exactly. Like, this is spooky stuff. It's the kind of code that unless you've been messing around with, a lot of kind of lower level operations, then you're not really going to know, right? It might take you a while to kind of puzzle out what is happening here and why. Down here, it's extremely obvious what's happening and what we're trying to accomplish. But here is another really important question, okay? Which one is uglier? Up here. But which one is faster? William?
Depends on your compiler flags.
Yeah.
Optimizations are equally the same.
Unfortunately, that's a good answer. You don't always know, depending on how your compiler is set up. In this case, though, most of the time, one of these for relatively large sample sizes or problem sizes is going to be way faster. Which one?
It's probably the top one.
Yeah, it's probably the top one. Okay, the lecture is kind of driving you to that conclusion, but I'm going to prove it to you, okay? So here you can see me doing experiments like last night as my eyes are falling apart and I'm falling asleep. I wrote an experiment here that uses randomness. How many steps are this actually? Like millions. Is that 100 million? How many zeros are there? Yeah, I think that's 100 million, okay? We're going to generate 100 million random numbers, and then we're going to feed them into this absolute one function, which does this funky bit math in order to get an absolute value. And let's go ahead and we're using Chrono, which I'm going to show you in just a little bit, in order to kind of quickly do a quick and dirty bit of testing. So here I'm on the one compiler website. I run this code. We're only using absolute one, and we're getting like 1.8 seconds, 1.9 seconds for 100 million of these, 1.7 seconds. I was too lazy to write some code to run it 10 times and choose the median or the average. So I'm just kind of getting a feel for it and clicking, right? Now we say, okay, it's like 1.6 to 1.9 seconds. I'm going to change this to 2. So now we're doing the much more human-readable version of this, which most notably has a branch, okay? This one up here doesn't have a branch. It is getting the answer without doing any sort of logic or conditional logic. Look at that. We got a 2.4. That's bad news, all right? But maybe we were unlucky. Run it again. And it's even worse, 2.5, okay? This is a pretty big performance win. Now, I don't know if maybe this problem size of 100 million is not realistic, but we can see that at least for big problem sizes, absolute one, this funky, nasty-looking function really pounds. Absolute two, the more readable function. If you are doing a lot of absolute value operations, this is a big optimization for you, a huge one. By the way, why does absolute one work? Does anyone know? I found this function, and I was kind of shocked to see what it actually did. And I think what is happening is it's taking advantage of how integers store the negative kind of part of that integer. And what I think it's doing is it's kind of shifting things over so that it knocks out the negative sign, basically, in the integer data structure, and then kind of shifts things back to fix the number back up in this second line and returns that, which is pretty awesome. Okay, I really wish I was a lower level engineer when I see stuff like this. because it's really very impressive. But I think that's what's happening, and that's what the intuition is. I'm not sure about that, though. Okay, go study it and let us know. A big problem here is this branching. And one really interesting problem I ran into last night is that initially in this testing code, I wasn't generating the number we were feeding in randomly. What I was doing is I was iterating from like negative 10 million to positive 1 million and putting them all in a row. And in that case, guess which one of these was faster? Guess which one? Number 2. Number 2 was noticeably faster than number 1 when the numbers we were feeding in were predictable. Why? How can this be true? Yes?
Branch prediction.
Exactly, branch prediction, right? So our compiler and our hardware, our processor is very smart, and it is kind of trying to predict, like, should I go down this first branch or the second branch, and when? Well, when you feed it a really predictable input, like just iterating right through all the negative numbers and then into the positives, you just nail it pretty much every time. The condition basically isn't even here anymore. And so it can run super fast. And the kind of memory manipulations happening here are actually a little bit slower than the branch predictor and what it can do. But if you randomize the numbers, like what we're doing currently, and you feed in a random number, the branch predictor can no longer help you very much. And it is much slower than the first one. So a question for you: which one of these is the more realistic scenario? Take your absolute value function. You're in a game. Do we know if it's going to be a positive number or a negative number? Can we know this consistently, or is it going to appear more random to that function? It's kind of hard to say. You know what you should do? Profile it. Okay? You don't always know what's going to end up being faster. And you can do a lot of theorizing, but the way a compiler and hardware decides to finalize things, like, is going to make a huge difference. Okay? It could blow you up. It could blow your expectations away. So these kind of tricks are called optimization tricks often because they are kind of unintuitive and they are obscure, right? Runtime performance can improve dramatically when you employ these kind of things, but dev time performance tends to fall apart. Okay? A junior programmer, an intern on the programming team, runs into code like this and they're dead. They're going to lose hours. All right? Wondering if the bug is in here and then poking at it to try and figure it out and fix it. If you have written this, they can easily fix this, okay, if there's an error in this somehow. And so I want to emphasize what I've emphasized a few times already. Do not focus on optimization too early. Sometimes if you know you're going to have great performance in an area, you will start to do some things to make that possible later. But in general, you want to focus on correctness way before performance. And then performance kind of comes on as you need it. It's very easy to, in the last few weeks of development, replace your absolute value function with this thing. Okay? And boom, easy, free performance. And no one needs to look in this function ever again. We verified it works. There you go. It's done, right? That's a really good time to optimize. Like I've said earlier, many times a game will be seen at trade shows before launch and the performance will be crappy. The game will not be running on console. It'll be running on a Alienware computer behind the curtain. And only like the weeks before launch will the team go hard in the paint on performance and get it running in part by obfuscating and doing all these hacks. And so it becomes very hard to optimize, to continue development, but it becomes very fast. This is a huge problem for a certain genre of game these days. In the past, you could have this beautiful readable code base for 90% of development, and then at the very end, when you're done adding content, you can optimize it. The code base is now ugly, very fast though. Why is that a problem for live service games and MMOs? This is a big problem.
You have to patch that after.
Yeah. Yes, with live service games, MMOs, games that consistently get new updates, new content, you can't just obfuscate and add hacks to this code base that people are going to have to keep using and developing on top of, right? So that's one big problem. It's one of the problems that makes live service such a difficult situation for developers, okay? So, anyway, I want to talk briefly about complexity, right? Nothing you don't already know, but I want to introduce you to one really fun, very famous example where complexity isn't everything. So you've seen this before. In general, anything that is kind of sort of accelerating upward as the problem size grows is not really considered acceptable. And in many cases, you can kind of find solutions to this that are at least linear or log linear. Log linear is kind of like sorting algorithm, right? And sometimes if you need to do something like traveling salesman problem for whatever reason, you can say, well, we're going to accept non-optimal results. Like we're going to accept approximate solutions, and the user won't be able to tell anyway. And that's going to be much faster, right? Much better complexity. But complexity is one of the first things you always think about when you're going for optimization, right? It is a huge, juicy, low-hanging fruit, and for very good reason, right? Scalability is extremely important in many of our applications. If you write a suboptimal algorithm in EECS 494, no one cares. Your problem size, very small. But if you want to go work at Google, if you want to go work at Jagex with thousands of players on their servers playing RuneScape, suddenly that N is pretty big. And you need to make sure that your algorithms are scaling appropriately. However, I think you've learned about complexity and how scaling is important in other courses. What you may not have learned is that it doesn't tell the full story. Okay, there are other things to consider, and you do still need to test stuff. Why? Well, I want to talk to you briefly about matrix multiplication. So kind of in a naive, right, just doing these multiplications and additions, these dot products kind of algorithm, you're going to do kind of work on the scale of N3. Okay? So as your matrix grows, you get this pretty nasty growth that is like quadratic. Not very pleasant. That's not good. And so there's a big question here. Well, what if we could find an algorithm that was not n to the 3, but like maybe n to the 2? Ooh, all right. That would be much better, right? Would it be much better? Yeah, it's like Austin, like you're trying to set us up, man. You'd think it would be much better, wouldn't you? Right? So I want you to show you, there's an entire Wikipedia page for this matrix multiplication problem. And the fact there are a lot of algorithms that exist for matrix multiplication. And it seems to me that a really good way to finish your PhD or to get your theory lab to be famous and get some funding maybe is to try and lower your exponent. Okay, so you find ways to lower it to like 2.8. That's good. That's something, right? How about 2.5? These days, right, we are lowering it to 2.3, and like, oh my gosh, look at how close they are to each other, right? Like thousandths of a decimal place. So which one of these algorithms do people use? Which one would you want to use?
Really depends on the constant values.
Well, that's not very in the spirit of big O notation, is it? Right? Usually we just ignore the constant values, right? So that's the really fun, ironic thing about this particular problem. The complexity gets so much of our attention for a very good reason, but those constant terms actually matter. Okay, when you step away from theory and into the world of actually making good software that people use, good products. So what ended up happening is apparently, if you're going to use any of these, you're almost certainly using Strassen, the 2.8 exponent. Or in some cases I saw you're actually just using the naive algorithm, but with some optimizations to kind of get rid of some multiplications or something. The reason here is that you have to do so much kind of setup and work on the side for these lower exponent algorithms that you actually need a problem size that is bigger than any input set you would ever find on planet Earth. And so for it to be worthwhile, for the lower exponent algorithm to start winning the performance battle. And so this apparently, I learned this last night, there's a term for this, galactic algorithm. And it's kind of like this competition in academia. It's like this intellectual exercise. Because while you can lower this number, and you'll learn some cool things doing so, you'll never use these unless humanity expands deeply into the stars and our data sets become much larger. And there are quite a few different galactic algorithms that you can kind of look into here. This is all to say that you should think about complexity, but you should always test, because sometimes finding a way to lower complexity is going to wreck you in the short term. Okay, have you ever heard of a function called std sort? Have you ever used this? I think you might have used like std stable sort or something in one of your homeworks. I don't know if this is true, but I heard it was the case that for large, problem sizes, it will use, I think, merge sort or some sort of merge sort that is like an n log n complexity algorithm. But apparently, if your n is small, your input size is pretty dinky, it will actually not use that. It will use like insertion sort, like a quadratic n to the 2 algorithm, which is crazy. But it's doing this due to simply practicality. Insertion sort apparently is quite a bit faster to set up and get rolling than a merge sort. And so, smart, right? So again, this is all to say that care about complexity, but don't let it dominate everything that you're doing when you're trying to optimize stuff. In particular, I'll say one more thing about complexity. This isn't really complexity related, but a lot of students, a lot of times when a student is struggling on performance test cases in this particular course, it's usually because you're doing work you don't need to be doing. That's often the case. You're comparing objects to other objects you don't actually need to be comparing to. You are calculating a result, but you're not reusing that result later on in the same frame. That kind of thing is a real killer. And it often doesn't affect the complexity, but it can cut the amount of work you do in half, which is quite a nice thing, even though that doesn't show up in the big O notation. Okay, so, all right. Local testing is kind of an important thing. This is the main file, the main function for homework 9 staff solution. And you can see here we've actually set up kind of a fun little define situation. The preprocessor is going to help us out. What we have here is we have some code wrapped in an if-def and end-if. In fact, I think there was a question about this on the previous quiz. Basically, this code will only exist to the compiler if this performance test symbol is defined, i.e., this doesn't currently exist. I need to get rid of this comment, these 2 slashes. And when I do that, this block of code will turn on, and this block of code will also turn on. And when I do something like this, I can get some pretty fun information. I want to show you this real quick. So let's go in here to main.cpp. I have kind of a big test case I'm running, and I'm going to run it right now. And you notice inside of here, I just have my little engine class, and I create the engine, and then I just kind of call into its game loop. And that's it. Let's go ahead and run this code and just kind of see what happens. Whee! It's a particle system. You're like, what is this? This is a particle system performance test. It's not supposed to look good. I have some other test cases that look good. This one does not. Okay, so we've run it. We know it works, but now I'd like to get a little bit more quick information about its performance, all right? And so let's go ahead and run this again. And there we go. It's running, it's running, it's running. And then we're going to get a number at the end of this test case. This gives us, right, 4,289.85 milliseconds. All right. This is a very rough way to measure performance. We could run this again and see if it performs better or worse. It probably will be quite different. But this is kind of a quick way for you to get a feel whether you're headed in the right direction or not. You can, if you want to, you can run this code, this function, put it in a for loop, and then at the end, divide it by 10, divided by however many times you ran this, and you have a rough average of the time it took to complete this game loop. What I want to do, though, is that this is not a great way to test the performance of your software. Because on the autograder, we're going to speed everything up. We're not actually going to perform a render to the screen. We're only going to render to disk. We're also not going to enforce a 60 frame per second delay between frames. When you call render and present, do you know that function? If you look inside of it, it's actually going to stop your execution. It's going to sleep for a bit and wait till the next frame shows up. What you need to do to get a good performance read is go to helper.h and then turn autograder mode to true. This will give you the most authentic autograder testing experience as possible, i.e., you won't hear any audio and you won't see anything on your screen except the black window. Okay, here it goes. There's also an environmental variable you can enable to do this instead of having to recompile everything. Here we go. And, yep. Okay. There you are. I think it's about the same performance, but I don't know if that's the case on the autograder. We'll have to see. So you can do local testing using this kind of chrono package in this fashion. It's not too hard. You can create a clock data structure, and then that clock is something you can kind of test. So you can use now and then now again, and you'll get two timestamps, so beginning and ending one. If you take the ending one and subtract the beginning, you'll get a duration, and then you can print that duration if you want to get the millisecond count. There's some other things you can do if you want to get an even more precise thing, like nanoseconds. I don't really care that much, though. This is just very loose. And so you can do it in that fashion. Another thing you should be thinking about is how to generate your own test cases, because not all test cases in this course are downloadable, and there's a decent chance you might want to make your own. For instance, this test case has like millions of actors in it. I did not hand write the location and the properties of these actors. Okay, you're never going to believe it, but I don't have time for that. And so how did we create this test case? Well, I created a Python program. Once you know what the general structure is, the JSON file structure is for creating these actors and these scenes and the properties they can have, the range of properties, you can write a Python program that will generate one of these basic scenes, one of these files. I think this is literally like that particular file. Look at how long it's taking. This is ridiculous. Okay, it's 200 megabytes, so you know it's beefy. Let's open this up in Notepad++, see if it can handle it. Oh no, uh-oh, I shouldn't have clicked on that. Oh, here we go. Okay, so why is it called Crazy Crossing? Is that the right one? Well, it's a similar scene in any case. Is that really the right one? Yeah, it is Crazy Crossing. Okay, did I give you the wrong one? I think I might have. Yeah, this is because this is not the visual test case. This is for homework 4, I think. Anyway, right, all these different things, the different dialogue, the different blocking states, true or false, the views, the positions, the actor names are just incrementing one by one. But we have a gigantic test case, and what's important is that I can tweak the test case. For instance, I could put all of these actors on the same exact position to see how my game engine handles a pathologically evil test case, where every actor is on the same cell or in the same region for homework 6, okay? You can do a test case yourself where you say, hey, I'm going to make all my actors small except for the last actor, which will be gigantic Chungus squirrel. And we'll see how my region system handles this kind of pathological evil test case. Not a bad idea. You get that kind of control that you wouldn't have if you're just using my test cases when you write your own. And if you're curious, this is the Python file, not very big, that helps me generate these things. So let me see here. We have our main function. Well, Python doesn't quite work that way, but we're going to generate a scene. We've got these little tweakable numbers I can mess with toward the bottom of the file. How many actors? How many different types do I want? What are the dimensions of the scene? I can generate this scene, which is a big, basically, dictionary. That's what JSON it basically is. And then I can dump this scene Python dictionary as a JSON file. Boom, done. All right, I don't have to worry about syntax or writing strings or stuff like that. I can put options in here, so randomly choose one of these dialogue options. And there you go. Pretty nice, right? Okay, I think I want to show you one last thing when I got the time. You could grab this if you want to. It's right here. You can use it for future test cases, customize it, whatever you want. I want to show you the profiler real quick. Okay, I've got this very difficult Homework 9 performance test case. I'm switching into autograder mode, but I want to know more information. I know that I am taking, a certain number of milliseconds, but I want to have really good information about which of my functions are running slowly. If you can, I've heard it's better to run this in debug mode because the symbols make a bit more sense. But I was very naughty when I made this homework, and I made the mistake all the students make where I customized my release configuration but forgot to do the same for my debug. So my debug is broken. Like, I just can't use debug. So we're running with the release, okay? I'm going to go to debug. I'm going to go to performance profiler. And I'm going to check these boxes. I want CPU information, GPU. I want memory usage, right? That often is very related to performance. So let's click start. It's going to run my test case, big, good, long test case to collect performance data during. And then, the program is going to end, and Visual Studio is going to kind of start looking through this data file that it has collected. Right? It's going to take a few moments, and we're going to get 3 tabs for each of those things I asked it to look into. GPU information, down here. Memory usage, CPU usage, okay? You click on it, it's going to load that information, all right? And you can start to get some information about what is going on. So you can kind of look through, where's the game loop? Okay, rendering. It looks like rendering is a really kind of painful part of my engine right now. I can look through the call tree, right, which is, I think, my favorite thing to look at. And I can kind of see, what parts of my engine are taking all the time. I've got 99% of my engine time happening in here. Well, I can just kind of go down the tree, and I see a little bit of time is in this, whatever on earth this is. I think if you use debug configuration, you have a better name here. I have no idea what that thing is. Well, we can see that SDL main, our main function, is taking up quite a bit of time. Destroying the render is taking some time. But I've got 3 functions here. I've got render and clear all images, a big function in my ImageDB, 34% of my time. Okay, that's a big one. But SDL render present in the helper is also taking quite a bit of time. I'm calling this, I think, quite often, which could be a problem. Maybe I'm calling it too much. Let's go into my function a little bit more. I'm using render copy X quite often. I'm doing a stable sort. That stable sort is eating up 4% of my performance. And that's quite painful. I've got a function called get texture, which is slower than I'd want it to be, taking up 1% of my time. When I open this up, can you tell me what is slow about my get texture function? Just by looking at this right here. You don't need to know much about it, but look at this. Yeah. Yeah. the way that my function works is that I send in a string with a name of the image file, and it has to hash that in order to look in a dictionary. O of 1 lookup, but hashing a string is slow, okay? And it has to do that to look in the dictionary to figure out whether or not we have the image already, and it returns it if so, and if not, it loads it and then returns it, okay? So you can kind of go through this, and you can get kind of a nice feel for what could be going on. One fun thing with sorting, sometimes you have to sort. You just have to. But you can save a lot of time within your sort if you can find a way to remove things that don't need to be sorted. Or if you can find a way to kind of get the array into kind of a not quite sorted, but like a little bit more sorted, right? So it doesn't have to do as much work to move things around. You can often speed up your sorting quite a bit using that kind of pre-organization step, okay? A prepping step. So anyway, this is a powerful tool. I know nothing about the Xcode profiler. I know that Ravi Bhatt, one of my previous assistants, loves it. You know, I'm not spending any more time in Xcode than I have to, but you can look into it if you want to. If you're an Xcode kind of person, go for it. If you got a Mac, go for it. Otherwise, use these machines here. They're going to have these tools as well. On Linux, there's GDB, there's CallGrind, Valgrind, and a bunch of other programs that can kind of help you with this. But it's my feeling that if you profile and optimize on one platform, there's a good chance you're going to get performance benefits on all of them. That's not guaranteed, right? But it's a good thing to try. So, anyone have any questions about any of this? And then the last thing I'll tell you, this one I think is less practical for us. And, you know, I said I would show you this, but then I realized I don't think most of us could really make use of this. Compilers do strange things when you optimize your functions. And here's kind of an interesting tool. It's called Godbolt. You can write functions like the square function here, and you can actually see the assembly for a particular compiler. It says GCC 15.2. Is there a clang in here? Of course there is, right? There are quite a few clangs, okay? Good luck finding the one you want. But you can actually see kind of what the compiler is going to do, and I think you can even tell it what kind of optimization level that you want. In any case, in the old days and for real deal, like in professional grade optimization engineers, like they will do this, right? They will look and study how compilers are transforming their functions, and they'll make sure that compilers are kind of doing the things that the dev intends for them to do, right? So avoiding making copies and stuff like that. It might be of interest to you if you really want to develop those low-level skills. If you do develop them, you'll be a very rare and valuable person indeed. I look at this and I'm like, yeah, I'm not going that hard. Sorry. I'll stay with my gameplay engineering, C# language. It's so nice. I'll let the compilers just have their way with my code. But back in the day, a lot more knowledge existed. A lot more people understood assembly because they had grown up learning assembly. That's all they used for their games, and then C++ arrived. And so there was this really crazy generation that had the ability to really optimize things in assembly, and they had a need to because the early C++ compilers stank. Like, they weren't very good at optimizations. So you'd have to get in there and do them yourself. It's pretty crazy, right? Anyway, so this is all to say that I think performance is one of the more, interesting things about this course. But it is very much an experimental thing. I think that is the main takeaway that you should have. You want to test. You really want to test. You don't want to believe things and just call it a day and make the commit and push. And then later you discover that you just wrecked your own performance by 50%. Okay? So over time, you'll start to get a feel for what makes things fast. There's one more thing that William was also talking about back there that makes things very fast if you can do it. But this is a little bit more of a topic in line with data-oriented programming, which we'll start to get to on homework 8 and homework 9. The basic idea is when you can make objects small, you can really make your programs kind of cache friendly. And there are ways you can get blown up by this, but it's a general good heuristic that if you can keep your data structures small, you can pack more of them into cache, which means going to your slower parts of memory much less often. Okay, cache misses, that's called. Okay, everyone, have fun, go forth, fight the good fight. Remember, you don't need 100% on homework 6. In fact, I might say it might not be worth it, okay? Get to 90% grade on homework 6, and then go enjoy your life, okay? And get ready for homework 7, okay? All right, I'll be around chilling here for 2 hours. And then I'll be here on Sunday in a few days, all right? And yeah, see you later. Okay. All right, everyone online and watching the recording, I will see you later. Take care, everyone. Bye-bye.